Okay class, welcome to this next section. So this is design of steel structures. I'm Engineer Ronjon Argarming. So today we are going to discuss threaded rods and cables. So threaded rods and cables is often used as tension members in suspended roof systems, hangers, or suspension members in bridges. Rods are also used as bracing system like Sagrads in purlins and cross bracing between trusses. In some cases, rods are pretensioned to prevent slack when the external loads are removed. So when we say slack, it is more on sag, okay, to prevent sag. Okay, so therefore, if we have rods used as a tensile member, when the member is released, these retention provisions will prevent slack from happening. So let us have here some configuration of threaded rods and cables. In here, we have a cable that is being used to support the suspended member system. Okay, there will be an open socket here. So this is what we call open socket connection. So this is the detailed anchorage wherein we have here the open socket, okay, that is serving as a lock system on the hole. So there will be the presence of steel plate or washer, and this is being drilled through the structural member. So another configuration is wherein the rod is directly welded to a certain plate, and a rod that is connected to a purlins. So this is what we call Sagrads. So it serves as a bracing system on the purlins of your roof system. It's normally threaded, or if not, that is welded through the purlins. So another connection is the clevis. So the clevis has the presence of the threads, just like the bolted connection here in the rod. Okay, so the concept here is that there will be a developed stress on the threaded portion. So normally, if we have threads on a certain rods, upsetting provisions are normally required to upset. Okay, so to upset that space occupied by the threads, of course, there will be a reduction of the cross-sectional area due to threading. So the upset end are normally greater than those section without threads. So upsetting is actually the enlargement of the cross-sectional area on the threaded portion. Now, cable are made of individual strands that will be made as a rope-like structure. So it could be in terms of the strand or a wire rope. You can see here that strand cable are consisting of several cable strands, while a wire rope is actually joined by a certain rotation. Okay, so I think you've also seen those type of cables. So in here we also have tension members in roof trusses. So in roof trusses, we have here the whole configuration wherein there will be a purlins. Of course, purlins are normally placed for the roofing system. So the roof covering will be placed on these purlin structures. And the purlin structures are normally inclined, that is connected to a truss. So here is typical inclined purlins. Of course, there will be a rod or sagrads that will be connected to serve as a bracing of your purlins. So normally, gravity loads are in the vertical orientation, wherein there will be need for calculation of the components, because our sagrads here are inclined with respect to the diagonal member of the top bottom. So on your truss, also we have the ridge. On the ridge, we also have a bent rod in order to brace the two series of purlins on each side of the truss. Now, with respect to that mentioned stress due to threads, so this will be the thread, there will be a stress area in it. So the stress area will be incorporated in the nominal area. So of course, the nominal area are those sections without threads, and the relationship between the stress area and the nominal area is that normally the stress area is only 75% of the nominal area. With this, we can just recall the formula for the nominal strength Pm. For the load resistance factor design, we have this expression, that the design strength should always be less than or equal to phi times the nominal strength Pm. Hence, we have 0.75 Pm. And the nominal strength will be given by the formula, the gross area times Fe. In here, we'll just have to replace our gross area to 75% of the bar area, since we have a stress area on the threaded portion. So therefore, we can now simplify our equation solving for the required bar area on the stress section. Likewise, for ASD, we have this expression that the allowable load should always be less than or equal to the nominal strength all over the factor omega. And that factor omega, if you may recall, that is equal to 2 when we are dealing with a fracture section. So PA now will be given by the equation PA is less than or equal to 0.5 times 0.75 of the area of the bar times Fe. Similarly, we can determine the area of the bar in terms of the allowable loading. So the area of the bar will be equal to PA all over 0.5 of 0.75 Fe. So notice here that we have already utilized this similar equation, only that we have 0.75 factor to the fracture strength, because of that the stress area is equal to 75% of the nominal area. So moving into the problems, first we have a threaded rod is to be used as a bracing member that must resist a service tensile load of 2 kips dead load and 6 kips live load. In here, we are required to determine the size of the rod if we are going to use 836 steel. Now for Lrfd, of course, we're going to use the factored loading. So the factored loading that will be prevailing here is 1.2 dead load plus 1.6 live load. We substitute the given loadings. We have 1.2 times 2 plus 1.6 times 6. We will yield to 12 kips as the factored load, and that factored load will be incorporated in the calculation of the required area on the stress with threads. So the bar area requirement will be equal to PU all over 0.75 multiplied by 0.75 times FU. Substituting the given, we have PU is 12, we have FU of 58, we'll be having a required area of 0.3678 square inches. Now calculating the area of the bar, the required diameter will be equal to 0.684 inches. So this, we can use 3/4 inch diameter of the rod. For ASD method, the variation here is the calculation of the allowable load. In here, we simply barely add those loadings. 2 plus 6 is equal to 8. That is the allowable load for ASD. Hence, we apply our required bar area, which is equal to PA all over 0.5 times 0.75 times FU. So again, we substitute the values. We have 8 all over 0.5 times 0.75 times 58. So we will yield the bar area of 0.3678. So this is the required bar area. So if you notice, simply happened that Lrfd, ASD yielded to the same values of the required bar area. So therefore, we can simply use the same required diameter. So we use 3/4 0.75 inches, that is actually greater than that of the required diameter 0.684. So this is the required size of the rod given 836 steel will be used. So we have here the notation. To prevent damage during construction, rods should not be too slender. Although there is no specification requirement, a common practice is to use a minimum diameter of 5/8 inch. Now 5/8 inch is around 0.625. So another problem, we have here a fink truss that is spaced at 20 feet on centers, support W6 by 12 purlins. By the way, W6, the 6 constant there refers to the estimated depth of the section, while the 12 is referring to the weight in pounds per feet. So the purlins are supported at their midpoints by the Sagrads. We're going to use here a 36 steel and design the Sagrads and the tie rod at the ridge for the following service load. Metal deck, we have 2 pounds per square foot. Build-up roof, we have 5 PSF. The snow load will be PSF of horizontal projection of the roof surface. Purlin weight is 12 pounds per feet. Length, as we can see on the code, W6 by 12. Again, 12 pounds per feet is the weight. So here's the illustration. Notice that we have an inclined member of the truss on both sides. The truss has a total width of 90 and it is symmetrical. The diagonal length is 46.6 and the ridge height is 12 feet. So first, we're going to calculate the loadings. So in here, the tributary width for each Sagrad will be 20 all over 2. To explain that, the fin trusses are actually spaced at 20 feet. So if these are the trusses, of course, half of 20 is 10 because this is 20, and according to the problem, your purlins are supported at the mid of that 20. So therefore, the tributary width for each Sagrad will be 10. Now, the tributary area for the deck and build-up roof will consider this shaded portion. So the inclined length is 46 and the spacing is 10. So therefore, the tributary area for deck and build-up roof for each Sagrad, that is 10 feet width and an inclined length of 46. So 10 by 46.6, we have 466 square feet. Now moving on to the calculation of the dead load. Of course, we're going to use here the tributary area that was already calculated. All we need are the values of the dead loads. We have 2 PSF and 5 PSF. So that will be simply added and then multiplied by tributary area for the deck and build roof. So we'll yield to 3,262 pounds. So moving on to our next dead weight is the total purlin weight. So the total purlin weight is 12, calculated by the unit weight, 12 pounds per foot or length. So therefore, we have 12. Okay, so the purlin from the unbraced length is 10 feet, as you can see in the figure. And here we have 9 purlins on each side. So we have to multiply it by 9. Hence we come up with 1,080 pounds. So therefore, the total dead load, you just have to sum 3,262 and 1,080. And that will yield to 4,342 pounds. So moving on to the tributary area for the snow load. Because in here, it is a provision that the snow load will be on the horizontal projection. though we have here the inclined member, we have horizontal projection. Therefore, we're going to consider the length that is horizontal. So notice that this length is half of 90, that is 45. Therefore, the tributary area for the snow load is 10 coming from the width and that would yield to 450 square foot. So therefore, the total snow load is 18 PSF times the area 450, and that will be equal to 8,100 pounds. So therefore, we have already came up with the values of the total dead load that is equal to 4,342 pounds and a snow load of 1,800 pounds, 8,100 pounds. So, utilizing these calculated values, we are now determined to apply Lrfd. First things first, we're going to use the combination here involving dead load and snow load. Of course, out of these two combinations, combination 3 controls. Always that among the combinations of the loadings given, we should choose the larger. Now for Sagrad and for tie rod at the ridge, we should compute for the forces. For the member forces, of course, this red line here is the axis of your Sagrad. In our calculation, the total loading is 18.17. So that will be in terms of kips, that is going downwards. So what we are trying to do here is to calculate the force on the Sagrad, because the Sagrad is inclined on this truss. So granting that this is the inclined length, 46.6, so this is the force that will be induced on the rods. That is actually just a component of your 18.17. So let us label this as the force at the Sagrad. So of course, we should have to complete your force triangle by connecting a perpendicular line to the Sagrad to the end of the vertical weight. So in here, we'll just have to utilize the slope of this inclined member. So we have here a vertical slope and a horizontal slope of 45. So this shall develop an angle of your Sagrad axis up to the horizontal. So say we name this as theta. So utilizing our slope here, we label this as theta. We just simply draw a vertical line. So here we have an inclined surface, theta, vertical, and a perpendicular line to that inclined surface. This is also theta. So with that principle of trigonometry, if this is the vertical line, this is the perpendicular line, therefore this is also theta. We need to establish that angle to calculate the component T Sagrad. So therefore, T Sagrad is equal to 18.17 as the hypotenuse multiplied by the sine function, wherein sine of theta is equal to 12 all over 46.6. 12 is actually the opposite of theta, and 46.6 is the inclined distance, which is the hypotenuse of your slope. So therefore, the force of the Sagrad will yield to 18.17 times 12 all over 46.6, and this will result to 4.679 kips. So our next task is the top of the ridge. Notice that in the top of the ridge, the orientation of the member is horizontal. Hence, with that, we're going to consider the axis of the purlins. And then from the axis of the purlins, we have just calculated the force of the Sagrad, which is actually parallel to the axis of your purlins. So T Sagrad here was just calculated to be equal to 4.679. Now the horizontal component, considering that we are getting the force on the top ridge, we label that as T top ridge. Of course, we know that this is also theta. So if this will be my x-axis, we'll just have to perform this equilibrium equation, summation forces x is equal to 0. Hence, 4.679 is towards left, that will be denoted by negative, plus the component of the T top ridge multiplied by cosine theta. Now cosine theta here is 45 all over 46.6. So this will have to be equal to 0. Solving for the T top ridge, we have 4.679 transpose to the other side. Of course, this will just be inverted. 46.6 all over 45. So therefore, the top ridge tensile force will be equal to 4.845 kips. So in here, our concern is the forces on the T top ridge and the Sagrad. Knowing that our calculated forces are the following, we have T top ridge 4.845 kips and 4.679 kips. We can now compute the required bar area for the Sagrad. Using Lrfd, of course, we have this equation. The force is divided by 0.75 by 0.75 by Fe. So we simply substitute the values here and come up with the required bar area, 0.1434. So in here, if we're gonna try to use 1/2 rad diameter, computing the bar area using that diameter by the formula pi r squared all over 4, we will have 0.1966 square inches, and 0.1966 inches is greater than 0.1434. So we might say that it is sufficient. However, for a bar not to be slender to avoid construction damage, 5/8 diameter bars is used as minimum. Therefore, instead of using 1/2, because of that provision, we're gonna use 5/8 diameter. So computing now the bar area of that cross-sectional area or diameter, we have 0.3068, very much greater than the required bar area of 0.1966. Now for the tie rod at the ridge, we use the same formula. This time, we'll just have to substitute the force on the top ridge, and that force was actually computed and is horizontal. So the required bar area will be equal to 4.845 all over 0.75 by 0.75 by 50. Therefore, we can arrive at 0.1485 square inches. Just the same, we use 5/8 diameter, even though 1/2 rod diameter is appropriate. Now, for the ASD calculation, again the variation would be the factor load or the load combinations. So on the load combination, we barely add dead load and snow load. That is 4,342 plus 8,100. So all in all, we have a load of 12,440 pounds. So this shall be used in the calculation for Sagrad and for the tie rod at the ridge. Just the same, we will use the same principle of the inclined force on the Sagrad. Of course, we utilize the given W, which is 12.44 from ASD, the sum of the dead load and the snow load. So this is the inclined member that would require an inclined force also. So this is the T Sagrad with the corresponding slope. The corresponding slope is again 12 vertical and 45 horizontal. We can name this as theta. Vertical and perpendicular, this is also theta. So with this vertical calculated force, this is the vertical and this is the perpendicular line, therefore this is theta. By principle, T Sagrad will be equal to 12.44 times sine of theta. Wherein sine of theta is opposite over hypotenuse of 12 all over 46.6. So 46.6 is the inclined dimension, which is actually the hypotenuse. T Sagrad is equal to 12.44 times 12 all over 46.6. T Sagrad is equal to 3.203 kips. So moving on to our ridge force. So the top ridge force for tie rod, we have to consider the inclined axis of your purlins so that we can calculate the horizontal component present on the top ridge. So in here, parallel to the rotated x-axis is the T Sagrad, equal to 3.203, I should say. And then we have the horizontal force for the tie rod at the ridge. And if this will be my x-axis that is inclined at a certain angle theta. So we use the equilibrium equations along that x-axis. We have negative 3.203 that is towards left, and a rightwards counter force from the force of the top ridge. This shall be multiplied by cosine theta. So we need to multiply that by cosine theta to get the component horizontal x of your T-top ridge. So in here, cosine theta is 45 all over 46.6. So this shall equate to 0. So therefore, the T-top ridge is equal to 3.203 times the reciprocal of cosine theta. So we will yield to a value of 3.317 kips. Now that we have known all of the force on the top ridge and the Sagrad, we are now ready to determine the required bar area. For Sagrad, the required bar area is equal to T Sagrad all over 0.5 by 0.75 times Fe. So we substitute all of the given and the acquired values here. Hence, we arrive at 0.1473 square inches. So again, obviously, your 1/2 rod diameter will surpass or will be greater than that of the required bar area. However, though sufficient for a bar not to be too slender to avoid construction damage, again 5/8 diameter bars is used as minimum. Therefore, we use 5/8 diameter. So to check that one, of course, we just calculate, and we have 0.3068. That is very much greater than the required bar area. Now for the tie rod at the ridge, again we use this formula. We have 0.5 by 0.75 by 58 as a denominator. Again, this is sufficient. So hence, we use 5/8 diameter bar, very much greater than your required. For the tie rod at the ridge, so we substitute the values and come up with a required bar area of 0.1525. Hence, though notice that 1/2 diameter rod will be sufficient enough for this requirement, we still use the minimum for avoiding construction damage. So that ends the problem. Thank you, class, and have a good day.